Okay, so this is chapter 19. I will post the homework. I've been a little behind. I got into a car accident over the weekend, so. Yeah, I'm fine. Just rear-ended. Smashed the back of my car.
Oh, that's it.
Yeah. Well, it could have been worse.
What car?
My new car, right? Oh, I know. That's what makes it so bad. It's like, new car, beat up. Okay, let's get started. Okay, we're going to talk about, have I covered any of this? Okay, good. So we figured out what aromatic is in the last chapter, right? And things that are aromatic are especially stable. Okay, so this is a theme to remember because stability is going to drive the way a lot of these reactions go. So just some ideas. Bromination reaction, you should know this, right? Anti-addition to a double bond of Br2. This is the product that you get over here. Ooh, yeah, it works pretty good actually. If you do the same thing with benzene, nothing happens. Okay. Do you remember what kind of reaction? Oops, sorry. This is work. Oh. Bromination, and it's is it not radical? Is it a got a
Halogenation?
no
Halogenation.
no it's a halogenation, and it's electrophilic. You guys remember that part? What is it? What does it mean that it's an electrophilic reaction? An electrophile? Well, what does it mean when it's an electrophile? It likes electrons, right? So what is it about Br2 that likes electrons? You guys remember? It's more stable, exactly. If you, I like this. Oh, I borrowed this from Mr. Balo. It's like probably a $30 crayon. Sorry. I'm going to change the colors too. Wow, it's so bright. Okay, so what is it about this, Br2, that makes it an electrophile? You guys remember? It's polarizable. It's the atoms are big. They have an electron cloud around them. And so as the electrons can shift back and forth, right, the density changes back and forth, you can develop a dipole. So it could be like that at one moment, or in the next moment, it could be like this. Wow, that's a big eraser. And when it's like this side of the molecule is electrophilic, right? And it can attack this double bond. It can pull the electrons out of the double bond in that moment. Okay, now, when we try to do the same reaction with benzene, right, nothing happens. So the question, right, why does nothing happen? It's aromatic, right? So the pi bond is more stable when it's aromatic. And as a result, the bromine's not electrophilic enough to pull the electrons out. That's so bright. Sorry. First day with new projector. It's like having a new toy. So all you have to do, though, in this reaction, and this is key because the mechanism of how this works, right, is going to always be the same for these electrophilic aromatic substitution reactions, okay? The mechanism's always going to be the same. If you add iron to it, instead of getting the addition product, that would be an addition product, because you get rid of the pi bond and you put something at both ends of it, instead you get a substitution, but this reaction goes pretty well, okay? You can make this happen. It doesn't take a lot to make it happen. So just a thought. You get substitution. That's the major product. Why do you think substitution is the major product? What's the difference between this and this? Huh? It's not resonance stabilized. And in this case, when it's resonance stabilized, right, it's aromatic. So there's resonance stabilizations, that's just delocalization. And then aromaticity is like a whole, it's like resonance stabilization on steroids, right? It's extra stable. And as a result, the difference between just this first product shown at the top and the second product is the aromaticity of the product. That drives it to be a substitution reaction rather than an addition reaction. Okay, so quickly, right, just I think you guys know this. It's called a substitution because you had a hydrogen there before, and now you have a bromine, okay? Oh yeah, I'll talk about that in a second. Okay, but here are some examples of electrophilic. Electrophile is the bromine, right? Aromatic, that's the product. The product is aromatic, the reactant is aromatic. Substitution, right? These are all the types, well, they're not all. There's a lot more types, but these are many of the types of electrophilic aromatic substitution reactions you can have. You can add bromine, you can add chlorine, you get a nitro group. This is a sulfonate, so it's a sulfonic acid. This is an R group, so it's just alkyl groups like methyl or isopropyl or T-butyl. And this is known as an acyl group, okay? Put a few of those names in there. So this is a sulfonate or a sulfonic acid. That's a kind of a new one. We're a little bit familiar with it because this is the cousin to toluene sulfonic acid with the chlorine on it that gets substituted when we produce a leaving group from an alcohol. So it's a relative to that. And this is known as an acyl group. Acyl simply means on the carbon next to the benzene ring, which we call the benzylic carbon, right? You have a carbonyl group. And then the rest of it's just an R group, an alkyl. Okay.
So the mechanism for all those are the same?
The mechanism for all of those is essentially the same. So to start with, Br2 is not a good enough electrophile. But let's just play the pretend game that we have an electrophile that's good enough, that's strong enough to pull the electrons out of the benzene ring. And what I'm going to do is I'm going to draw you the entire mechanism. Okay, I will repeat it several times as we do each of the reactions, and then at some point I'm going to say, hopefully you know what it is. All you really need to remember for all these reactions is how the electrophile gets formed. Okay? And then once you know how the electrophile is formed, the mechanism to the product is always the same. Okay, so I'll show you that. Hopefully it'll be clear. So let me make a blank slide. Almost blank. There, that's blank. And it's a remarkably simple mechanism. So I'm going to draw benzene. And on two of these hydrogens, two of these carbons, I'm going to put the hydrogens, but you know there's hydrogens all the way around it. I just want them to be there because as I draw the mechanism, they're useful to have there. Okay? All right. So electrophile, I'm just going to call it Y plus. I don't know why they call it Y. But that's like standard. Like the electrophile, almost always in every book is called Y. The only reason I could think of is somebody said, well, what's the reason? Why not? That's the only reason I could ever think of. So anyways. So the benzene ring is the nucleophile. Y is the electrophiles. Benzene ring attacks and the pi bond gets broken. We could break it a couple of different ways. I'm going to have the Y group attached to this one, but it could as easily attach to this one. It's just because of the way I've drawn the structure for the mechanism. So the first thing that you get is this structure. Now this thing has resonance, right? And at this point, you could do an addition reaction. That is, a nucleophile could come in and could attack here, but it doesn't, because if it does, then it's not aromatic anymore. You'll see that carbocation has resonance. By the way, does it make sense that I did it like that? Right? Just as a reminder, the electrons in this pi bond attack the electrophile. And when it attaches to one side, that means the electrons are no longer on the other side. That gives you the positive charge. So that's just reviewing back a little bit. Generally, when they draw this mechanism, they include the following resonance structures to help explain the stability of the intermediate, so that, and then one more, like this. And those are the resonance structures. You might have additional resonance structures depending on what you just added or what was already on the ring. So you could have electron withdrawing groups and additional resonance structures. But if we ignore all the other attachments, okay, those are the three resonance structures you get. And this is known as the sigma complex. I'm writing too fast now. And this is an important structure to know how to draw because it's going to explain a lot about reactivity later. So you just get in the habit of doing this. But at this point, okay, with the structure the way it looks, a base can come in and remove a proton. The proton it removes is this one. Ooh, you can even tell it's red. I just did that to see if you could see. And when it does that, it reforms the pi bond. Right? So a base comes in, attacks the hydrogen, a pair of electrons goes back to the ring, and what you end up with is your substitution product. And there's resonance structures for this too, but we don't usually draw them, but you could go back and forth. These double bonds could rotate around on the inside. Make sense? This is the same mechanism that we use for like 75% of the chapter. Okay. So what people usually like about this material is that it's easy to sort of get the hang of. And at the end, we're going to introduce some other reactions that happen on aromatic rings that have a different mechanism, but those mechanisms are all the same to each other as well. Well, not bad. Okay, so question is, a couple of things. This electrophile, what has to be true of that electrophile? It's got to be really strong, right? And strong, what do we mean by strong? Why does it react with benzene? Benzene's really stable. Really strong means the electrophile is essentially unstable and helps to pull the electrons out of the benzene ring. Okay. So now the question is, go ahead, George.
For resonance structure, isn't the first one and third one exactly the same?
First one and the third one. Not for resonance structures, because you're just moving the electrons. In terms of like structurally, like symmetry and all that, yeah, they're the same. But you have to draw the third one to show how it goes to all the carbons. If you were to stop at this point here, right, and say those are all the resonance structures, then you couldn't explain why there was an electron deficiency over here, for example. Right. So that delocalizes across the entire ring. Okay. So here's the mechanism. Here's the thing I want you to remember, okay? By the way, all you have to do in this reaction, oh, hang on. Got to pause and plug my computer in. Okay, so this is what I want you to remember. Like in this reaction, this first step is not that important, but if you can remember that iron reacts with bromine to make what we call ferric bromide or iron 3 bromide, that's fine. A lot of times it's just included as FeBr3. Okay? In other words, you don't have to add iron to the system, but adding the iron and then adding the bromine produces the reagent that produces the electrophile. Okay? So iron, metal ion, has d orbitals and is a good electron acceptor. And so in this first step, you see that the bromine attacks the iron to make this complex. The important part of this being iron is really that it is a metal. And most metals are good metal ions, because it's a +3 ion, is a good Lewis acid. Okay, so a good Lewis acid. So what happens is, when the bromine attaches to the iron, you get a negative charge on the iron and a positive charge on the bromine, which makes this bromine, okay, more electrophilic. The result is the bromine that's at the end is also more electrophilic. So, in essence, right, it's in equilibrium with structures like this where the bromine is essentially positively charged. Now, you know bromine, being a halogen, doesn't like to be positively charged, so it's really a strong electrophile. Okay, so rather than draw what's on, go through the slides, I'm going to draw it out so you can see this whole process. Oh, look at that. This is so amazing. So the first thing that happens is we'll draw benzene. And then we're going to draw our electrophile. I'm going to leave the hydrogens off. We're just going to assume that they're there now. Okay. I'll draw the hydrogen where I tack in again later. So my electrophile is this. Oh, come on. Sorry, I'm having to draw really slowly. Okay, that's my electrophile. This is the electrophilic atom. So the electrons break like this. And then you get that arrow. So that's how the bromine, that first step, the bromine gets attached to the ring. Okay? The rest of this structure, we'll invoke it later. We'll call it FeBr4 minus is later the base in this reaction, or generally is the base in the reaction. So it's going to pick up that proton at the last step. It's what usually picks up the proton. So what I've done now at this point, this is all of this in the earlier mechanism. That's Y. Okay. So what do I get? I get this. And at this point, you should really get in the habit of drawing the sigma complex. Okay? That's all the resonance structures. But I'll tell you, sorry, there's an H there. That oftentimes, unless the mechanism requires you to explain other products, you don't always need it. Okay, I'll show you that in just a second. Right, so now the base, which is really one of the BRs on that complex, okay, comes and attacks this, and then that bond goes like that, and that leads to the product. Well, that's a weird Y. What's the other thing that comes off because of the BR attacking the H? HBr, yeah. Yeah. Yeah, and then you get FeBr3. That's the other thing that you get. Because once you remove this Br, right, from this complex, you're back to the FeBr3, and that's why it's the catalyst for the reaction. You only have to add a little bit of it, or have a little bit of it present, formed in the solution for it to work. Okay? This is very similar to the acyl substitution reaction we did in lab the other day. Go ahead. Oh, sorry. Comes from that. It's on the previous slide. Yeah. So it comes from that.
So the pi bond from aromatic ring, it attacks the bromide, right?
Pi bond acts, yeah, the one on the end.
Yes, but why would it attack it if the other bromide is partially positive, or is positive? Wouldn't that make the other bromide very negative?
It means the bromine, okay, has a positive charge, means it needs a pair of electrons.
Oh, okay.
So
Right.
most likely to attack that, so
Yeah, so it is possible that this would attack from like here to here, but most likely this is the easiest place to attack, and when you do that, you get this is stable complex ion. If you attack it here, then this bromine has to come off, right? I don't know if it matters, but based on the mechanism and the product that you get, it's got to be something like this. Go ahead.
And do we have to use iron or can we use another metal? Or
You know, I'm pretty sure if you substitute like aluminum in here, a lot of other metals will catalyze these reactions. Well, we used it for, and you'll see why we used it for a reaction. It's very similar to the acyl substitution reaction we used in lab last week. Do you remember what the gas was? Like you had that gas trap. Do you remember why you had a gas trap there?
we won't breathe it in?
So you won't breathe what in, though?
Hydrogen gas?
No.
HCl.
It was HCl. Yeah, the reactions produce a strong acid. Those strong acids a lot of times go into the gas phase, especially HCl because it prefers to be in the gas state. Okay? So that's why you have a gas trap for a lot of these reactions where you don't breathe it in. Nice. Okay. Oh, yeah. Sorry. And so what I wanted to mention is... Go ahead.
For previous slide, you made it seem like it happens stepwise. First, the leading group forming the bromide positive cation. And this one, it looks like it's concerted where the pi bond attacks, and then the second bromide receives the pi bond, the sigma bond electrons. Which one is it? Is it this one that's concerted, kind of with the attack, and then the...
Oh, yeah. This is a rationalization for why this bromine is so electrophilic. Yeah. So it doesn't necessarily break, but it's such a weak bond that it behaves as if it's a cationic bromine, cationic bromine and an anionic complex ion. Okay. Just one other thing I wanted to point out here. I didn't have to draw the sigma complex to finish the mechanism. I can take it from here. Okay. So like I said, a lot of times you need to know that this sigma complex exists, but that also leads to the product. And the reason for drawing the sigma complex is just to understand stability, and a lot of times you get other substituents added in reactions just to help you understand why reactions happen the way they happen. Okay. All right. Again, you get the sigma complex, which is the intermediate, and then you have two choices. Your choices are addition product or substitution product, and you know that we studied heats of hydrogenation in the last chapter. Aromatic is much more stable than just conjugated two pi bonds. And so as a result, this substitution product becomes the major product because it's a lot more stable. Okay. Questions? Those are all good questions, by the way. All right, so we can use chlorine, and when they use chlorine, they typically use aluminum chloride. I really don't know what happens if you use aluminum bromide here. I don't know if you end up with any bromine in the product, because that would be an interesting problem too, because that would imply that it does that Cl-Cl bond breaks and then reforms in some equilibrium with free bromine, but I don't know how that actually works. Okay, so anyways, if you want chlorine on there, typically they use aluminum chloride. And so you use Cl2, aluminum chloride, 85% yield, similar to aluminum bromide and bromine. Okay. What's the mechanism? What's the first step or the formation of the electrophile? Yeah, I have Cl and Cl, and then I have Al, and then Cl3, right? This is the formation of the electrophile. Once you have the electrophile, the mechanisms run the same for both of them. What's the first step here? Yeah, the Cl attacks the aluminum, which is the Lewis acid electron acceptor, right? You have to remember, like these compounds, right? These are really ionic, right? So this is really a charged ion in the middle, surrounded by negative ions. That's why it's a good Lewis acceptor. It just pulls another pair of electrons. Once you do that, your electrophile is going to have a Cl, a Cl, an Al. Ooh, I'll just do it like this. That looks weird. I ran out of space. I'll just draw over the letters. That's negative. That's positive. That's the electrophilic atom. At the end of this process, right, when the chlorine pulls the hydrogen off of the benzene ring, you end up with HCl again. And aluminum chloride back, so you get your catalyst back, okay? I'm not going to draw the mechanism, but it's exactly the same. The first step with the benzene ring, I'll draw that in, right? If I have a benzene ring over here like this, that Cl is attacked by the pi bond. This bond breaks, you have the sigma complex, and then you have the elimination, you have your product.
Why does both Cls attach to the aluminum instead of just one?
Sterics? I don't know. You mean why doesn't it go sideways and attach both?
No, like because both Cls are attaching to the aluminum, right? But usually when one attaches, it would just be one, so the bond would break and go to the other Cl.
So like this one would break?
Yeah, that one would break off. But why is both of them?
It's a Lewis acid and a Lewis base. So if you remember, Lewis bases have lone pairs that just attach. So you remember complex ions in Chem 1b? Right? Metal ions attract anions to form complexes. So you're saying, why doesn't this, when this happens, why doesn't this just break off?
Yeah.
Well, there's nothing to, remember, something has to break it off. Something has to take it off of here for that to happen. And the thing that takes it off is the pi bond in the benzene ring. It pushes it off of the complex. And again, like they drew in that previous diagram, a lot of people just treat this as Cl plus and Cl. Because they break the bond, move the electrons to the Cl plus that's here, right? They just treat it like mentally, they treat it like this. And so you have a chlorine that's positively charged and a chlorine that's neutral with the negative ion. Go ahead.
Why is that bond so weak?
Because of the positive charge. Because the chlorine, right, is already bonded to the aluminum here. It doesn't want to carry this positive charge. So it's pulling on these electrons to help compensate for the positive charge. That makes this bond weak so that when this attacks, it can break very easily. But it's the weakness of this bond, which is the instability in the electrophile, that causes it to, the benzene to be able to attack it.
So it's not the chlorine atom on the end. That's what's not really electrophilic. It's that bond that makes it electrophilic.
Yeah. Yeah. Okay. Okay, so we're going to run through the mechanism. They drew it already. All right. So there, sigma complex. Right. So you form the electrophile. You get the sigma complex. From the sigma complex, this attacks, forms HCl. Right. Aluminum chloride. Those things that aren't drawn up, and your product. Okay. So I want to skip these two in the middle. I'll come back to them. There's a reason. So sulfonation and nitration we'll skip, but we're going to talk real quickly about the Friedel-Crafts alkylation reaction. There's two classes. There's alkylation and there's acylation. Alkylation is when you have an alkyl group. Acylation is when you have an acyl group. They follow the same mechanism, more or less. Okay. So they're asking, is an alkyl halide an effective nucleophile for electrophilic aromatic substitution? The answer is no. If the bond isn't polar enough for that to happen, okay? So how do you make this bond weaker? You put in an electron withdrawing group, is possible, or you bring in a metal ion to bond to the bromine on the alkyl halide, right, to weaken that bond. You make it so that this pair of electrons wants to go back up to the bromine, and that makes it less stable. Okay? So, first example that they give, I don't know why they didn't do the bromide. First example they give is you just add aluminum chloride. Right? Secondary alkyl halide, you add aluminum chloride to the reaction, similar to what we did in the lab the other day, right? And then you add the benzene to it, and you get an electrophilic reaction. What do you think the mechanism looks like? It's the exact same thing, okay? You're going to have your alkyl halide. Oops. Let me draw it. So I'm going to draw it like this, RCl. You have your aluminum chloride. First step, chlorine attacks. Remember, it's got all these electrons on it I didn't draw. Chlorine attacks the aluminum, forms this guy. The electrophile, it's created because the purpose of this aluminum ion, the Lewis acid, is to not weaken this bond. It's to form the complex ion with that bond. It's to weaken this bond. So your electrophile in the reactions is R group.
So what's the difference between this and making a Grignard's reaction? Because in the Grignard's reaction, the Grignard's reagent, you add a magnesium, right?
Yeah.
A bromide,
Yeah.
alkyl halide. Wouldn't also weaken the bond between the bromide and the
but doing this makes the R group an electrophile, and in a Grignard, what ends up happening is to stabilize the R group, the magnesium and the chlorine end up switching places, and so then the carbon that's attached to the magnesium is a nucleophile. Okay. People ask these questions like that, and you're like, well, there really is no difference. It's just all mechanism. But there is a big difference, right? Functionally, what happens? If you think about principles, well, you're forming positive charges and negative charges. It's kind of all the same. Okay, so here's the mechanism. So what can happen in these reactions, which often does happen in these reactions, this bond is so weakened by so the complex ion, you remember complex ions have formation constants. The Kf for this complex ion is pretty big. So when it forms, it's stabilized enough that this bond is weakened that it can actually break and become a cation. Now it only breaks and becomes a cation in like tertiary and secondary, and in primary it doesn't break, but we'll talk about that. It can still rearrange. Okay? So you get this carbocation, and carbocations are very good electrophiles, right? They're unstable, 6 electrons in the orbital there, got a positive charge. And so that is your Y. Mechanism. All right, I'm not going to show I'm going to show the full mechanism after the formation of the electrophile. I'm going to draw the carbocation like that. What's the first step? Pi bond attacks, right? You end up with like this. Full mechanisms means draw a sigma complex. I'm going to do this so you remember that there's a sigma complex. Sorry, a little bit of laziness there. And then the base, which is the aluminum chloride, will attack that hydrogen and reform the pi bond. Like that. Now, that can't be that basic, but it turns out this is really acidic. That's why this works. Why is that really acidic? Because when it loses the proton, it's aromatic. Okay. So the aromaticity drives this reaction forward to form this product. And the base doesn't really have to be that strong because the hydrogen, when it's pulled off, makes the ring aromatic.
ALC3 or ALCO4 minus?
Oh, this guy. So this will pull it off. One of these chlorine bonds will break and pick up this hydrogen. That's where the HCl gas comes from the reaction. And then you end up with aluminum chloride again, and it's a catalyst. That's why you add the aluminum chloride once. You don't worry about it. It just stays in the reaction as the reaction proceeds. The only thing you have to worry about is all the HCl gas that comes off the reaction. Especially if you don't set up your little thing right. I've only done this on a microscale. I can't imagine what it's like when you have like a liter of solution and how noxious that must be. Or how hot it might get, so you might have to really ice that thing down. I don't know. Yeah, so here's the problem. You don't form a carbocation on a primary alkyl halide, but the problem is you still get rearrangement. So that if you use a primary alkyl halide and you try to form this product, the majority of your product usually ends up being the secondary alkyl group rather than the primary alkyl group. Let's think about what happens when this reaction takes place, right? So this part of the reaction is essentially the same. That is, the chlorine's going to attack the aluminum. So I'm going to form something that looks like this. It looks something like that. That chlorine really wants to leave badly because that bond is so weak between the carbon and the chlorine now. So by pulling all that electron density away from the carbon, it makes the carbon unstable. It is enough instability that this hydrogen that's next to it shifts over, and then this breaks off. So what do you end up when you do that? You end up with a secondary carbocation. So you end up with that. Okay. But again, it doesn't really form the carbocation until this hydride shifts and then pushes this thing off. Okay. But then after that, the mechanism's the same. You've generated your electrophile. Electrophile attacks the ring. Aluminum chloride anion, right, attacks the hydrogen, removes the proton. You get HCl, aluminum chloride, and your substitution product. It's not really a hydride shift. It's a bond breaking with the hydride shift. Yeah. Go ahead.
Since it's forming carbocation, right? Would this be like inhibited if we were to do it in like a product solution? Or?
Probably. Yeah, it's probably faster in more polar solvents. On the other hand, too, you have to worry about if this was the structure. Once you get the carbocation, it'll rearrange potentially again, and you end up with the third product, and then it gets to be really messy. Okay. Yeah, so hydride shift, sorry. There's a slide. Okay. Three downsides to Friedel-Crafts acylation. One is you can't do these kinds of reactions. They have to be alkyl halides. They can't be vinyl halides. There are reagents for making, they're called coupling reactions. There are coupling reagents for adding vinyl groups directly to the benzene ring, but we don't really cover them in this class, okay? You know why we don't cover them? Now, it makes synthesis problems too easy. And then the mechanisms are so, I know, right? The mechanisms are so complicated. They involve transition metals and like 4 things attached to transition metal and a sort of a cyclic mechanism that goes like catalyst, product of the catalyst, catalyst, product. They're so complicated, you don't actually learn how it works. You just memorize, oh, I can make that bond. So the goal is, in organic chemistry, because I used to teach all of those reactions. I'd be like, oh yeah, this is like, there's a Heck reaction, a Still reaction, a Suzuki reaction. They're all known as named reactions. They're awesome, right? Only problem is you don't learn fundamentals. So then when you go to learn those reactions, you can't understand how they work. I learned them, just learned them, I don't know, somewhere. Reading, right, studying. I didn't learn them in my undergrad. Probably learned a few of them in my graduate coursework. And then some of them were new, so some of them I learned when I was teaching the class. I'm like, oh, this is a neat reaction. So then I'll tell you why I stopped teaching them. As much as I like them and occasionally I teach them, is, I send a lot of students out of here. A lot of them go into research or whatever. So I talked to some of the students, one in particular who went to graduate school for organic chemistry and got his PhD in organic chemistry. And I asked him what his opinion was, actually. What would you teach? What was taught to you in your undergrad? And he says, well, we basically skipped all those reactions because you don't learn any fundamentals from them. So then you learn them in your upper, like when you take, so believe it or not, okay, you can take organic chemistry, then you can take advanced organic synthesis, and that's where you learn those. So a lot of my students have finished organic chemistry and are like, oh, I really like this. So they actually took the class, advanced organic synthesis, like afterwards, for no particular reason. So anyways, bottom line is this was a student who went to UC Berkeley, and at Berkeley they don't teach them at the undergrad level. So I thought, well, It's one of the schools a lot of my students transfer to, so that's the model that I follow. And if you want to learn it, you can learn it in an advanced class. Okay. Yeah, so you can't do this, is the bottom line. So that's one problem. And like I said, there's a lot of reactions that do that we're not covering. Maybe not right away. Maybe I'll show you a couple next time or something. Here's the other problem. This is actually a big problem synthetically. Okay? When you're doing an alkylation reaction and you add an alkyl group, you can get what's called polyalkylation. Now, polyalkylation sounds fancy. It just means you add a bunch of alkyl groups. The reason it happens, okay, is this is an electrophilic reaction, and the benzene ring donates its electrons to the electrophile, and in the first step, it'll go something like this. Let me draw it out. In benzene ring, good, still recording, electrophile, aluminum chloride, you end up with benzene ring with that on it. What is the electronic character of alkyl groups? What do? They donate electrons. So what happens is this alkyl group donates electron density to the ring. So what does that mean about the electronic environment of the ring now? It has more electron density in it, right? So it's a better nucleophile. It reacts faster than the original benzene ring. So in this reaction, this is your nucleophile. This is your electrophile. If I could get this thing to follow my handwriting. That's the electrophile. All right. Now the nucleophile is attacking the electrophile. This is more nucleophilic. And as a result, it's going to attack another electrophile, but it's going to attack it faster. So then you get that second product that they showed. And in truth, this is probably the only other product that you get. So think about the problem. This reacts, forms this. This reacts faster than this does. Okay? It can be like anywhere from like 10 to 100 times faster because of the addition of the electron donating group. So you get that electron donating group. This one reacts faster. So guess before another one of these reacts with one of these, it makes this. So you end up usually with a lot of, if you can have a lot of alkyl groups, if there's room, this doesn't have room for a lot of alkyl groups, so it probably stops. But you have room for a lot of alkyl groups, you might be able to add a lot of alkyl groups.
Is the parity confirmation favored here because
Sterics.
sterics?
Yeah.
I was thinking about the partial charge on
No, ortho and para. Ortho is probably more favored electronically, but sterically it's less favored because that's a T-butyl group. But if it's a small group, generally speaking, ortho is, they call it the ortho-para ratio, like how much ortho you get versus how much para you get. Typically for small groups on the ring, ortho is favored, and then the larger the groups get, para is more favored. But some of that's controlled by can be controlled by temperatures and concentrations. And there's a lot of things apparently. So I always tell people, if you really need to know like how much of each one you get, you have to run the reaction, throw it in the GC mass spec, throw in some standards, and measure it. And then you'll know how much you get for your reaction conditions.
So then if we're just doing this mechanism on a test per se, and we're given either a T-butyl group, then we should just know it just.
Yeah, it's so big. T-butyl is so big that it's going to be para as the major product. You might have a little ortho, but I would guess that it's a fraction of the.
And if we had a smaller.
Yeah,
then it would
yeah.
work.
Like a methyl group, it's usually ortho. Okay. Okay. So you can get polyalkylation. And the other thing is that in these acylation or alkylation reactions, they're very sensitive to electron withdrawing groups. Like electron donating groups are bad. Turns out electron withdrawing groups are bad too, because the electron withdrawing group, like the nitro group, okay, pulls electron density out of the ring, and the ring can't be a nucleophile anymore. Okay, so you think about what nitro does. If you think about the structure of a nitro group, I'm going to draw it next to it. Let's get rid of it there so I can, oops. Let's get rid of it here, and I'm going to draw it here. Nitro looks like this. Okay. This positive charge pulls, and the resonance here pulls so much electron density out of the ring that you can't do acylation or alkylation reactions under those conditions. It turns out you can do sulfonations, a bunch of other things you can do, but you can't. It turns out you can't do Friedel-Crafts reactions. Okay, so summarize, right? Has to be an alkyl. Can't do it with vinyl. Get polyalkylation. And a lot of rings don't react under these conditions. Okay, so acylation, right? This is an acyl, that's an alkyl. Friedel-Crafts acylation reaction, look, same kind of thing, right? Chlorine, carbonyl group with aluminum chloride. What do you think the first step in the reaction is? Seal attacks the aluminum, right? It's a little bit different, but not that different. Chlorine attacks the aluminum. This bond breaks, and you end up with what's called the acylium ion, which is kind of a cute name if you say it over and over again. Sorry. So, oh, you're so acylium. I guess that's a side effect of still having small children. Or having never grown up, one or the other. The resonance for that looks like that. You notice that this is sp2 or sp hybridized there. This is still sp here, so it's not changing angles. Okay, it's sp hybridized. That's enough stabilization that if it's primary, it doesn't rearrange. Okay, so if this is your acylating agent, and you react this with aluminum chloride, you form that acylium ion in resonance with the other one, right? That's enough to keep the carbocation from rearranging. Oops, I drew it wrong. Okay, so those resonance structures mean then, since it doesn't rearrange, you can attach the primary carbon directly to the ring and not worry about rearrangement. And then, because you can't do that with alkylation reactions, And then what can happen is once you've formed the acyl group, turns out there's this neat reaction called the Clemmensen reduction reaction. It's essentially like a hydrogenation of the carbonyl group, but unlike hydrogenation that produces an alcohol here, the hydrogenation in the Clemmensen reaction completely removes the oxygen. So now you can have a primary attached alkyl halide. It just requires one extra step. Okay? What's that? I'm not going to go into it right now. I think it's just hydrogenate. So part of it is the H reacts with the zinc. Oh, so do you know? Okay, sorry. When they draw this, is probably the first time you've seen this. When you draw this, or you write that, what state is mercury in at room temperature? It's a liquid, okay? So mercury is a liquid at room temperature. One of the properties of mercury is that it dissolves other metals. So you can take zinc and dissolve it into the mercury. So you have a solution. This is actually a solution of zinc and mercury. Turns out, one of the reasons I don't wear my wedding band is I secretly try to not be married. No, I thought that would wake a few of you up. It's because I used to work in a lab that had a lot of mercury in it. And when you work in a lab with mercury, mercury will dissolve gold. In fact, that's one of the original applications of mercury, was to pull gold out of ore. They take gold, like gold ore, right? And then you throw in mercury and you shake it around and the gold dissolves into the mercury. Well, if you have a ring and you work with mercury, what happens is it dissolves your ring. And what you end up with, instead of having a gold band, you end up having a silver band. But the silver is not like platinum, it's like mercury. So then you have to dip it in nitric acid. Anyways, you got to clean it up. It takes a while. So long story short, in the lab I worked in, my uncle made my wedding band for me. He made it, but I couldn't wear it in lab because we had worked with a lot of mercury. And then I lost the ring a long time ago. I don't know where it went. So then I had to buy a new one, right? And then I couldn't wear that one because it makes it, I have fat fingers. Yeah, so she wears it. And she doesn't wear hers because she wears mine, and I won't go into that either. Okay, so this is known as an amalgam. Yeah. And the amalgam, when the HCl reacts with it, produces hydrogen gas. And the hydrogen gas, or hydrogen radicals in hydrogen gas, that reduces that bond. Okay? Okay, so interesting thing about alkylation reactions and acylation reaction, one of the big differences is when you do an acylation reaction, you only add one acyl group. Because, unlike an alkyl group, if this was an alkyl group, this reaction would happen again. This is an acyl group. What kind of group is this? It's an electron withdrawing group. So it deactivates the ring as soon as you add it, so the second one adds very slowly. I'm interested to see, because some people had to leave theirs in their aluminum chloride solution over the weekend. I'm interested to see how much of the other product that they ended up getting, actually. Probably, hopefully none. Okay, so back up. I'm going to go all the way back. The acylation, alkylation, sulfonation. Here we go. Fuming sulfuric acid has in it SO3. If you look at the electrostatic potential map for sulfur trioxide, this is what it looks like. So if you remember, right, red is negative, blue is positive, right? So this is the sulfur. These are the three oxygens, trigonal planar arrangement and generated on Spartan, by the way, of sulfur trioxide. There's a lot of positive charge in there. So you remember we talked about electron donating. One of the aspects of electron donation has to do with orbital size. Orbitals have to be of similar size for electron donation to be efficient. We talked about this a couple of lectures ago. So because the sulfur is attached to oxygens, the oxygens are more electronegative than sulfur, and the periodic table is just right above it, right? Bless you. So it pulls electron density back. If this had been a carbon, the charge wouldn't have been as high. Because what ends up happening is the oxygens try to donate electron density back to the sulfur, but the orbital size is different enough, like this, okay, is different enough that when it tries to donate electron density back to the orbital, it doesn't donate it completely into the orbital. So you end up getting a very electrophilic center.
Practically what you were explaining last week.
Yeah. So I was trying to say that generally it's important, but it's important as we go on. It's important for stuff like this. In the second half of the chapter, it's also important to understand halogens. Anyways, we'll get into that when we get to it. Oh, so first of all, I want to show you how the sulfur trioxide is formed. Because I think it is generally useful to know this. And I'm going to start with this. I decided this was a better way to do it. Equilibrium reaction. What am I going to get? Do you guys remember this one from Chem 1B? H3O and OH minus, right? That'll be positive and OH minus. Okay. How did that happen? Huh? Oh, I don't know how that happened. How did that happen? One's an acid, one's a base. This is going to make some of you go, oh my God. Like in Chem 1B, we always draw the proton moving, but in organic chemistry, we draw the hydrogen moving. But that's the mechanism for that reaction, right? That the oxygen attacks that hydrogen. You end up with a hydronium and a hydroxide. Now, to make fuming sulfuric acid that has SO3 in it, you just take sulfuric acid, pure sulfuric acid, and you heat it up. You boil it. Or you can boil it. You just need to heat it up, really, till it fumes. You draw the structure for sulfuric acid. What's he saying over there? Very loud. It looks more complicated. So I'm going to take that plus that. What do you think happens? What's that? One attacks the other, right? Acid base. And so the one on the left becomes this. I'm going to zoom in a little bit and draw it a little smaller. Becomes this. So one gets protonated, one gets deprotonated. how am I going to get SO3 out of this? Because that's where it comes from. It comes from the next step. Water's a good leaving group, right? And it's heated. It favors the leaving of the water. All I have to do is get rid of this hydrogen. I have this, right? This can come back and take the hydrogen back. Just like that. And so what I end up with after that whole process is SO3, because that's what you get on the left, right? H2O, which if you notice, if you combine these together, you get back to sulfuric acid, right? And H2SO4 comes back out of it. But this sulfur trioxide is the electrophile for the reaction. Okay? So, simple way to remember it, right, is it protonates, water leaves, that turns into sulfur trioxide. Mechanisms the same as you've seen. Electrophile, ring attacks, right? Sigma complex. So they drew all the sigma complex down here like this, right? And then the water, which is the strongest base in the solution, attacks the hydrogen and then becomes hydronium, and that protonates the sulfonic acid. So in essence, it's exactly the same, except the one difference being when this nucleophile attacks, there's a rearrangement of a bond in here, but otherwise it's exactly the same. At the end, it has to protonate, so there's another difference. Sorry, I forgot about this one. Protonate, and then you end up with your sulfonic acid. Okay, that's sulfonation. That turns out to be an equilibrium process. If you do it in concentrated sulfuric acid, you add a sulfonate group. If you do it in dilute sulfuric acid, the sulfonate group comes off. Okay? So that's what they're showing here. If you have concentrated fuming sulfuric acid, which let's hope we never deal with, you add the sulfonate group, and then if you do it under dilute conditions, then the sulfuric acid wants to come back off. It ends up coming back off. Right? And you get back to a benzene ring. The reason this is going to be useful later is it's a way to introduce an electron withdrawing group to a ring and then taking it back off. And if you remember from the lab, electron withdrawing groups are meta-directors. You can add a meta-director and then have it disappear. Okay? Okay. Hey, look at this. This is that lab we did, the nitration lab. Nitric acid, sulfuric acid, 50-50 mixture usually, right? It doesn't have to be, but usually. Here's the nitric acid. First step was sulfuric acid. Protonates, right? Produces a leaving group. Resonance pushes the water off, and you end up with the nitronium ion. But again, like sulfonation, it's the same mechanism. You protonate nitric acid, water leaves, you have an electrophile. I think there's a train going by, or there's another earthquake. Yeah, it's pretty regular. Wow, look at that vibrate. They told me it vibrates a lot, but it must be a train. Okay, mechanism, right? It attacks, sigma complex, it eliminates, you have your product. That makes sense? I don't need to go through the whole thing. Do I? I'll go through the whole thing. There's your sigma complex, right? And then a base attacks the sigma complex somewhere to form the aromatic ring back. All right, let's see. Couple of things that you can do with nitro groups, which is kind of fun. You can, again, reduce it, hydrogenate it, and form amines. Okay. Why would you want to do that? Electron withdrawing group, electron donating group. Okay, so you can change the nature of the substituent to control, which we will talk about in the next half of the chapter. We can control where substituents end up after this. Okay. All right, that's all I really have for today. Hang on, you're not excused.